Today, we're tackling a problem. Given a target array and a collection of smaller arrays, can we concatenate these pieces in any order to perfectly form the target array? It's a puzzle of assembly and sequence. The problem, check array formation through concatenation, gives us an array ARR and an array of arrays pieces. We need to determine if ARR can be formed by concatenating the arrays in pieces in some order. Each piece must be used at most once, and the relative order of elements within a piece cannot be changed. The challenge is matching the exact sequence. A naive approach might involve iterating through each piece and trying to find its starting element in the main array. Once found, we'd compare the entire piece to that segment of the main array. If it matches, we mark those elements as used and continue. This requires nested loops to search for each piece's starting point, and then another loop to compare the piece elements. This repeated scanning makes it inefficient, leading to a time complexity approaching O(n squared), in the worst case where n is the length of the main array. Space complexity would be big O of n for tracking visited elements. The key insight for optimization is that each piece is uniquely identified by its first element. If a piece starts with a particular number, that number will appear in the main array ARR only once as the start of that specific piece. This suggests using a HashMap. We can preprocess all pieces by storing each piece in a dictionary, using its first element as the key. This allows for big O of 1, constant time average time lookups. Then we iterate through the main array ARR. For each element in ARR, we check if it's a key in our dictionary. If it is, we retrieve the corresponding piece and verify if the subsequent elements in ARR match the elements of that piece. If at any point we don't find a piece or a mismatch occurs, we know it's not possible. We advance our pointer in ARR by the length of the matched piece. If we successfully traverse all of ARR, we return true. Let's trace this with an example. ARR is 15, 88 and pieces are 88, 15. First, we build our dictionary. Key 88 maps to the piece 88, and key 15 maps to 15. Now we start iterating ARR from index 0. The first element is 15. We look up 15 in our dictionary and find the piece 15. We compare ARR at index 0, which is 15, with the first element of the piece 15. They match. We advance our ARR pointer by 1. Now the pointer is at index 1. The element is 88. We look up 88 in our dictionary and find the piece 88. We compare ARR at index 1, which is 88, with the first element of the piece 88. They match. We advance our ARR pointer by 1. We've now processed all elements in ARR. Since we successfully matched all elements of ARR using the given pieces in the correct sequence, the result is true. We formed 15, 88 by concatenating 15, then 88. You'll spot this pattern when you need to match specific subsequences or blocks within a larger sequence, and the order of these blocks matters. The presence of distinct starting elements for each block is a strong signal for a HashMap, allowing quick identification and verification. This optimized approach has a time complexity of big O of n, where n is the total number of elements in ARR. The space complexity is O, P, where P is the total number of elements across all pieces stored in the HashMap. This pattern of using HashMaps for efficient subsequence matching is incredibly common. Try the next problem involving array reconstruction. Same pattern. Don't forget to like and subscribe for more DSA insights.